What if one metal could change the future? From ancient blue colors to the batteries powering our world, this is the story of cobalt.
Then, picture the incredibly powerful jet engines on a commercial airliner roaring at 30,000 feet.
Right. Totally different environments.
Exactly. And finally, consider the battery inside the electric vehicle parked in your driveway. Or, well, even just the smartphone sitting in your pocket right now.
I mean, it sounds like the setup to a riddle, right? Like, what single thread could possibly tie ancient ceramics, modern aerospace engineering, and the global transition to green energy together into one story?
Right. And the answer isn't a human inventor or some grand philosophical concept. It is one single, ordinary-looking metal,
Yeah.
a material that hides an incredibly complex and sometimes really dark narrative. So today's mission for our deep dive is unpacking the mystery of element 27, cobalt.
Yeah, and to ground us right at the start, I mean, if you were to just look at a pure piece of cobalt, you probably wouldn't think much of it, you know?
Just looks like a rock, basically.
Very much. It's a transition metal. It's hard. It has this metallic luster, and it possesses a bluish-gray appearance. On the periodic table, it sits right there in the middle, atomic number 27, chemical symbol Co.
You mentioned it's a transition metal. What does that actually mean in terms of how it behaves?
Well, that is a really crucial detail. So, transition metals are the elements found in the center block of the periodic table.
Okay.
And what makes them special is their atomic structure, specifically how their electrons are arranged. They have these incomplete inner electron shells.
Which does what, exactly?
It gives them this really unique ability to easily form bonds with lots of different elements and to share their electrons in highly adaptable ways.
Oh, interesting.
Yeah, that flexibility at the atomic level is exactly why cobalt plays so well in metallic alloys and, chemical batteries later on. But like you said, if you just held a chunk of it in your hand, it is, by all initial appearances, just a rock.
So how exactly did this rock evolve from an ancient curiosity into an absolutely critical material for modern civilization? Because to figure that out, we kind of have to look backward.
We do.
Because long before anyone knew what an electron or a battery was, humanity was using cobalt for a completely different reason.
Yeah, we have to step away from that hard gray metallic form entirely, because for centuries it wasn't prized for its strength or its conductivity at all. It was actually prized for its color.
Which is such an interesting contrast. I mean, you have this tough gray metal, but when it forms chemical compounds, it produces these intense, beautiful shades of blue.
Exactly. We are talking about a pigment so chemically stable and so brilliant that it has been used for millennia. Like ancient Egyptians used cobalt compounds to tint their glass.
Wow, that long ago?
Oh yeah, you see it in Persian ceramics and famously in the glaze of Chinese porcelain. For hundreds of years, artisans were grinding up these cobalt-rich minerals to create absolute masterpieces.
But they didn't know what they were working with, right?
No, they didn't actually know what the element itself was. They just knew that this specific type of ore gave them a perfect magical blue.
Right. But here's where it gets really interesting. The story of getting that ore was not magical at all. The name cobalt doesn't come from some ancient Latin word for the color blue or anything like that. It actually comes from the German word cobalt.
Which, if you know your folklore, translates to a mischievous spirit, or like a goblin.
Yeah, a goblin. I looked into this and I was trying to understand the leap here. Why would medieval miners name a beautiful blue pigment after a goblin?
Well, picture medieval miners in regions like Saxony, right? Working deep underground in the 16th century. They would strike these veins of ore that looked incredibly promising.
Like they hit the jackpot.
Exactly. To the naked eye, the minerals looked exactly like rich silver or copper ores, so the miners would haul them up and put them into the smelting furnaces, fully expecting to extract all this valuable silver.
But it didn't work.
Right. The ore would trick them. It wouldn't yield the precious metals they actually wanted.
So it was a fake out. But naming it after a goblin implies malice, not just a disappointing day at the smelter.
Oh, there was definitely malice, chemically speaking anyway. When they heated these specific ores, they didn't just fail to produce silver. The processing would release these dangerous, highly toxic fumes.
Oh, wow.
Yeah, what was actually happening, which of course they didn't know at the time, was that the cobalt in the earth is frequently bound together with arsenic.
Oh, that's not good.
No, it's really not. They form geological bonds underground due to the presence of sulfur, creating minerals like cobaltite. So when the miners roasted the ore to melt it down, they were basically oxidizing that arsenic and creating arsenic oxide gas.
So it was literally sickening and sometimes killing the miters.
Exactly.
So it's not a magical curse or a literal goblin. It's just chemistry acting like a poison. It creates the most gorgeous art for the wealthy above ground, but for the miners trying to extract it, it's just a toxic hazard.
And that reputation held for a long time. It was a material entirely defined by mystery, frustration, and folklore. That is, until the 18th century, when the Age of Enlightenment started pushing back against all that superstition.
Right, science steps in.
Yeah, in the 1730s, a Swedish chemist named Georg Brandt decided to rigorously study these goblin ores.
He essentially brings scientific order to the folklore, right?
He did. Brandt utilized really rigorous chemical isolation techniques. He was able to separate the mysterious substance and prove that the blue color wasn't coming from bismuth or copper, which is actually what the scientific community assumed at the time.
Okay.
He proved it was a completely distinct, previously unknown metal. He named it Cobalt, honoring the folklore, but basically stripping away the magic. He firmly established it as a distinct chemical element.
So element 27 is officially on the books, but I'm trying to connect the dots here. We have a toxic rock that makes delicate blue teacups in the 1700s. How on earth does that end up being used in the most aggressive, extreme machines humanity has ever built?
It's a huge shift.
Yeah, because moving from a ceramic glaze to a jet engine turbine seems like a massive leap in material science. Wouldn't a delicate glass colorant just melt or shatter?
It totally seems counterintuitive, I know.
Yeah.
But it all comes back to that transition metal flexibility we talked about earlier.
Right, the electrons.
Exactly. As engineering became more advanced in the 20th century, metallurgists started mixing different metals together to create alloys. They discovered that when you use cobalt as a base, creating what we call superalloys, something remarkable happens at the atomic level.
Okay, let's unpack this. What actually happened?
Well, cobalt atoms share their electrons in a way that creates an incredibly rigid crystal lattice.
So we are talking about aerospace now. Jet engines.
Precisely. Just think about the environment inside a commercial jet engine turbine for a second. The temperatures inside that engine frequently surpass the actual melting point of standard steel.
That's terrifying, actually.
Right. Furthermore, the turbine blades are spinning at thousands of revolutions per minute. The centrifugal force alone is literally trying to tear the metal apart.
So you need a material that basically refuses to stretch or melt under conditions that would liquefy almost anything else.
Exactly. In metallurgy, there's a concept called creep.
Creep!
Yeah. Creep is the tendency of a solid material to slowly move or deform permanently under the influence of persistent mechanical stresses, especially at extreme heat.
Okay, so it's like the metal stretching out.
Yeah, if you look at it closely, creep is just atoms slowly sliding past one another because the heat gives them the energy to move and the physical spinning provides the pulling force.
So the metal stretches like taffy?
Exactly like taffy. And in a jet engine, if a turbine blade stretches even a millimeter, it hits the casing and the engine catastrophically fails.
Oh, wow.
But cobalt-based superalloys resist this. Their atomic structure remains locked and stable. The cobalt atoms essentially pin the crystal lattice in place, preventing the other atoms from sliding past each other even when the metal is glowing white hot.
That structural stability is fascinating. I mean, the exact same element that was tinting delicate glass for centuries is locking atoms in place to prevent a jet engine from tearing itself apart mid-flight.
Yeah, its ability to maintain useful properties at very high temperatures made it completely invaluable to modern aerospace and demanding industrial environments. Without cobalt, the modern aviation industry as we know it simply could not exist.
Which is an incredible legacy all on its own. But the very structural stability that makes aerospace possible is what makes cobalt so irreplaceable in the next technological leap.
Oh, Cavani.
Because aerospace was just the warm-up act. The next chapter didn't just put element 27 in the sky, it put it in your pocket, in your home, and maybe even in the electric vehicle sitting in your driveway.
We're talking about the global battery revolution.
Yeah, we are absolutely surrounded by it. Smartphones, laptops, massive grid-scale energy storage systems for solar and wind power. Suddenly, cobalt isn't just a specialty metal for jet engines. It is the fuel of the wireless green energy world.
Right. And what's fascinating here is, well, we need to understand the mechanism of how a battery operates and why cobalt is so essential to it. A battery isn't just a bucket that holds electricity.
Right, it's chemical.
Exactly. It's a carefully balanced chemical environment. In a lithium-ion battery, you have lithium ions physically moving back and forth between two electrodes, the anode and the cathode, every single time you charge and discharge your device.
So the lithium is doing the actual moving, carrying the electrical charge.
Yes, the lithium ions are the travelers, but the cathode, which is the destination for those lithium ions when the battery is discharging, needs to be made of a material that can absorb and release those ions without physically falling apart.
Okay, that makes sense.
And many of the most energy-dense lithium-ion battery chemistries use cobalt in their cathode materials, usually in the form of lithium cobalt oxide.
I was actually trying to visualize this mechanical stress. If the lithium ions are moving in and out, I picture the cobalt as like the structural steel beams of a skyscraper.
Oh, that is an excellent way to conceptualize it.
Yeah. So if the lithium ions are like thousands of people working in a building, during the day, when you're using your phone, all the people rush into the building. They fill up all the rooms and the hallways.
Right.
Then at night, when you plug your phone into charge, all the people leave the building and go back home to the anode. If you don't have strong steel beams, like if you don't have the cobalt anchoring the structure, the constant physical rushing in and rushing out of the lithium would eventually cause the whole building to crack and collapse.
That is precisely what happens in lesser battery chemistries. The cathode literally physically swells and degrades over time. Cobalt provides that critical structural stability at the atomic level.
Just like the jet engine.
Exactly. Its geometry allows for layered structures where the lithium ions can slide in and out smoothly over and over again thousands of times. And on top of that, it helps the battery hold more energy safely, preventing thermal runaways or, overheating.
So that structural integrity is why your phone battery doesn't just degrade into a useless brick after a month of use. But, and this is where the story takes a serious turn, because we literally cannot build these modern dense batteries without that specific atomic structure. We are forced into a massive geographical bottleneck to get it.
Yes, we are.
We cannot talk about the triumph of electric vehicles and smartphones without talking about the reality of the supply chain.
The geographic reality of cobalt is heavily concentrated. While it is found in various places around the world, a massive share of the global cobalt supply historically comes from one specific nation, the Democratic Republic of the Congo, or the DRC.
The DRC holds enormous, just unprecedented cobalt resources in a geological area known as the Copper Belt.
It does. And the sheer scale of the mining boom required to feed the global battery market has raised intense, very well-documented concerns. Our sources point out that the extraction process involves severe environmental damage in the mining regions, including water contamination and landscape degradation.
Right.
Furthermore, there are incredibly poor working conditions associated with parts of this boom.
Yeah, and we have to be really clear about the facts the sources detail here. While a lot of cobalt is mined industrially with heavy machinery, a significant portion comes from what is called the artisanal mining sector.
Right.
These are essentially informal, unregulated operations where people are often just digging by hand. And within those parts of the sector, there are severe, documented risks of human rights abuses, specifically including child labor.
It's a very harsh reality that has been repeatedly highlighted by human rights organizations and international watchdogs. And the challenge is really compounded by the fact that global supply chains for these minerals are incredibly opaque.
But why is it so hard to trace? Like, if a huge tech company wants to buy clean cobalt, can't they just buy it from the industrial mine and ignore the unregulated ones?
In theory, yes, but in practice it's not that simple. Artisanal ore is often sold to middlemen who pull it together with ore from various other sources.
Oh, I see.
Yeah, this pooled ore is then fed into massive industrial smelters, primarily located in other countries, to be melted down. Once the rock is melted and refined into pure cobalt, you cannot tell the atoms apart. The unregulated material is baked right into the regulated material.
Wow.
So by the time it reaches a battery manufacturer, it can be nearly impossible to trace the exact origin of every ounce of the metal.
So what does this all mean? We are looking at a really heavy contradiction here. On one hand, you have the entire world trying to transition to cleaner transportation. We want electric vehicles to reduce carbon emissions.
Right.
But on the other hand, the physical materials required to build that cleaner future come with a very real human and environmental cost.
It forces us to ask a tough question. Can a technology truly be considered sustainable if its supply chain involves human suffering? It is a paradox that the tech and automotive industries are currently wrestling with on a massive scale.
So it's a supply chain issue as much as a battery issue. How do we build our way out of this? Because we can't just stop building batteries and go backward to fossil fuels.
No, absolutely not. The energy transition has to continue. But the industries are attempting to adapt through a multi-pronged approach. First, There is a huge push for supply chain transparency and responsible sourcing.
Which means trying to untangle that smelting problem you mentioned earlier.
Exactly. Using technologies like blockchain to track materials digitally and conducting rigorous third-party audits to ensure that battery manufacturers are attempting to source cobalt from mines that adhere to strict environmental and labor standards.
So it's an effort to force the global market to value human rights as much as it values the metal itself.
That's the goal.
But what about just engineering our way around the bottleneck? If cobalt is the essential steel beam in our battery skyscraper, can we just build the building out of something else entirely?
That is the second major palm, new battery chemistries. Material scientists are working around the clock to engineer cathodes that rely less on cobalt, or just eliminate it entirely. The most prominent example right now is the rise of LFP batteries, lithium-ion phosphate, which don't use cobalt at all.
Wait, I'm confused. If cobalt is so uniquely suited to locking the structure in place, how do iron and phosphate manage to do the job without the battery collapsing?
It's a great question. Basically, LFP batteries don't use that layered flat structure that cobalt provides.
Okay.
Instead, the iron and phosphate create a completely different molecular structure that resembles a rigid three-dimensional tunnel system.
Oh, interesting.
Yeah, it is highly stable and very safe. The trade-off, though, is that this tunnel structure is bulkier and heavier. It just can't hold as much energy in the same amount of space.
So an EV with an LFP battery might have a slightly shorter driving range, but it is cheaper and entirely bypasses the cobalt supply chain.
Exactly. So there are trade-offs, but science is trying to design our way out of the problem. But there's a third solution, and this is a big one.
What's that?
Recycling. I want you to think about this space sitting in front of you, or maybe the junk drawer in your kitchen.
Oh yeah, everyone has one of those.
Right. The drawer that has 3 old smartphones, a dead laptop, maybe an old tablet.
The modern domestic treasure chest.
Exactly.
But is recycling those old devices actually economically viable? Or is it just wishful thinking? Because I imagine extracting tiny amounts of cobalt from a crushed-up phone is incredibly difficult.
It is difficult, sure, but urban mining is rapidly becoming a massive and viable industry. The economics actually make a lot of sense when you look at the numbers. The concentration of pure, refined cobalt inside an old EV battery or a batch of old smartphones is somewhere between 10 to 20%.
Okay, and compared to natural ore.
Compare that to the richest raw ore in the ground, which usually contains less than 1% cobalt.
Wait, really? Oh wow, so your junk drawer is a significantly richer mine than an actual mine in the earth.
Precisely. Through advanced shredding and hydrometallurgical processes, which basically just means using liquid chemicals to dissolve and separate the metals, we can recover those valuable materials and put them right back into the supply chain.
That makes total sense.
If we can scale up battery recycling infrastructure globally, we close the loop. We keep using the same cobalt over and over.
Which is amazing. If we connect this to the bigger picture and step back to look at the whole journey of this single element, we started with this hard, bluish-gray rock, a transition metal just sitting in the earth.
Element 27.
Right. It was this mysterious ore that poisoned medieval miners and spawned legends of goblins. Then it was a beautiful pigment, painting ancient glass and Chinese porcelain with these stunning stable blues.
Yeah.
Then a Swedish chemist drags it into the light of modern science and actually identifies it.
Then it gets forged into superalloys, utilizing its unique atomic structure to hold together the glowing hot turbines of jet engines at 30,000 feet, resisting immense thermal and mechanical stress.
And finally, it shrinks down. It becomes the microscopic structural scaffolding inside the batteries that power our entire digital and electric lives. And it triggers a massive global mining boom, forcing humanity to look in the mirror and ask incredibly hard questions about the true cost of our technological progress.
Cobalt's story really is this intricate web. It connects ancient art, chemical discovery, heavy industry, aerospace engineering, the electric vehicle revolution, and the urgent push for global sustainability. It is, in many ways, a physical mirror reflecting the evolution of human civilization itself. It's a material caught in a transitional phase, acting as the bridge between the fossil fuel technology of the past and the truly sustainable technology we are trying to build for tomorrow.
The mineral has been identified, the goblin has been named, the technology to harness it is already in our hands, powering the device you are using right now to listen to this.
Yeah.
But as material scientists work frantically to engineer new chemistries that don't need it, and as we pull it out of old electronics to avoid mining more, it leaves you with a really strange thought. If we successfully transition away from it to save costs and protect human rights, will element 27 quietly fade back into obscurity? Will this extraordinary metal just become a goblin sleeping underground again, waiting for the next civilization to discover its magic all over again?